to electricity. As usual, we'll first look into what are piezoelectric materials, since these are the behavior of these materials is the foundation for the coupling we will investigate. This will be a volume coupling. So we will go into the governing equation, derive the finite element formulation, and then discuss the discretized system we obtain, and also detail a few of the modeling assumptions that we typically take when we model piezoelectric systems. Okay, so the piezoelectric effect was discovered in 1880 by Jacques and Pierre Curie, and it facilitates a coupling between the electric and mechanical field. And it's used in various applications. You see here a few pictures. It's used in the inkjet printers, printing heads. It's used in servo drives. It's used as in technical applications as active vibration damper, or in automotive injection actuators. It can be used, or it's frequently used, in so-called micro electromechanical systems, MEMS devices like surface acoustic wave filters. You see a picture here. And it can also be used in sports equipment, usually as passive vibration dampers. So here again, a list that's of course not exhaustive. You might also think about sensor applications, since we can convert mechanical into electrical quantities using the piezoelectric effect. This is used in microphones, accelerometers, and force and pressure sensors, for example. It's also used as an ignition device, for example, in lighters. It's used in servo drives or piezo motors. It's used for liquid dosage in the automotive sector for fuel injection, for example, as vibration dampers, as I already mentioned, in active or passive form, and very importantly, in MEMS devices, for example, surface acoustic wave filters, or also viscosity sensors or loudspeakers, micro loudspeakers. So what materials are actually piezoelectric? We can classify them into three classes. The first one is single crystals like quartz, silicon, oxide. These are isolators. They have no free electric charges, and they show a distinctive dipole structure, which is responsible for the piezoelectric effect. Then there are piezoelectric or ferroelectric in general ceramics, like barium titanate or lead zirconate titanate, PZT, which is actually one of the most important classes. So these class of materials are technically the most relevant. They show a rather strong piezoelectric effect, and the polarization that is responsible for the coupling in the end can be reversed by an external electric field. What is important is that these materials are only piezoelectric below the Curie temperature. So if you heat them up too high, they lose their piezoelectric properties. And finally, there's also a few polymers like PVDF that show piezoelectric behavior. However, this is typically rather weak. Okay, so how do the properties of ferroelectric materials lead to the piezoelectric effect? So for ferroelectric materials, it's important that they have a multi-scale structure. So you see here the structure ranging from the unit cell of a crystal. Here, as an example, the tetragonal unit cell of PCT material, which has a central ion here that has actually a few stable positions. So it can be positioned here at the top, it could be positioned here at the bottom, on the left or on the right. And depending on the position of this ion, the polarization of this unit cell is defined. And then the next level is actually the ferroelectric domains. So these unit cells, they're aligned next to each other, and typically we have here the single crystal, and within the crystal we have domains that have the same orientation of these ions, so the same polarization here denoted by these little arrows. And there are only a few possibilities in which these domain walls are energetically admissible, so they can only be 90 or 100 degrees with respect to each other. And furthermore, since these ferroelectric materials have a crystal structure, you can see here we have the crystal grains where we have the regular crystal grid as shown by the unit cell, and we have grain boundaries and a different orientation of the crystal grid in the adjacent grain. So you can see this structure is rather complicated, and if we want to actually model devices in engineering sizes, we need a sort of homogenized macroscopic formulation for this material behavior, since otherwise we would have to resolve this fine grain behavior back to the unit cell of the crystal, which is computationally, of course, not feasible. So we'll aim for a macroscopic formulation. And this is given by describing a macroscopic polarization. So what is polarization? The electric polarization describes the volume density of electric dipoles. So we have a lot of dipoles in our domain, and they show a certain orientation. Just note that only electric isolators can be polarized, and the electric field is actually the cause for the polarization. And polarization only occurs if all these many dipoles align to a common direction and therefore create a net polarization in the material. Here we have the dipoles, and when we apply our electric field, they're initially randomly oriented, and we apply an external electric field here shown by the positive and negative charges at the electrodes. The dipoles will align and thereby create a macroscopic polarization in our dielectric material. So let's look at the macromechanical behavior of piezoelectric material. After we have initially, it was typically, we'll focus first on the electric field versus polarization in the material. Typically, we start from zero electric field here somewhere in the center of this hysteresis loop. And if we apply an electric field, we'll go up here, the virgin curve, which is not depicted. And at some point, the polarization will saturate here. And if we don't then decrease the electric field again, we'll actually go down on this path of the hysteresis curve. If we start increasing it again, we'll go on the other branch of the hysteresis curve. You can see that when you take away the electric field, there's some remnant polarization remaining here. So at the 0 point of the electric field, and this is typically the point where we start operating our piezo actuator in the unipolar range. So we apply electric field and take it away again, and then we will transverse here on this unipolar cycle, and this is the behavior. This is defining the behavior or the technically relevant behavior of the piezoelectric material. And in this range, you can actually linearize the piezoelectric material behavior. So keep this in mind if you apply a linearized piezoelectric material law. This is often useful. However, it is not always accurate, especially if you don't have a unipolar actuation. When you look on the so-called butterfly curve that describes the mechanical strain versus the electric field, then you see that when you increase the electric field, also a strain arises in the piezoelectric material. And also here, when you transverse from all the way from very negative to very positive electric fields, you actually form this complete butterfly curve. And if you only operate in the unipolar cycle, you get this part of the butterfly curve, which again can sufficiently accurately be approximated by a linear material law in many cases. Okay, so how is this constitutive law usually derived? The entry point is the total differential of the Gibbs free energy. You can write it here as the parts of heat energy, mechanical energy, and electric energy. For the sake of completeness, I've given here also the tensor notation. So the strain tensor, of course, is the second rank tensor, as is the stress tensor. So we have here a double contraction. And here we have the inner product of the vector of the dielectric displacement and the electric field. And then from this equation, we can obtain the expressions for entropy, strain tensor, and electric flux. So the entropy is defined as the differential of the Gibbs energy with respect to temperature at constant electric field and constant stress. And similarly, you might be, as a mechanical engineer, more familiar with the definition of the mechanical energy. This is the wrong symbol here. This should be the strain here, is the total Gibbs energy with respect to sigma, and additionally here, the dielectric displacement we get as the Gibbs energy derived with respect to the electric field, and the other two quantities, temperature and sigma, are held constant. So if you do this now and write these equations insert these relations in the equation beforehand, what you get is this set of equations. And here you can actually recognize that the different derivatives lead to the physical material tensors that couple the different physical quantities. So these derivatives here we have the heat capacity, here we have the piezocaloric effect, we have the electrocaloric effect, we have here a familiar term, which is the elastic compliance matrix that we get with the double contraction of sigma. We have the piezoelectric coupling tensor, couple tensor, and here we have another effect we've seen already. This is the electric permittivity. So here we have in the second line, again here the symbol should be S, the constitutive law for mechanics. If we disregard thermal expansion, or if we disregard piezoelectricity for start, we have the familiar equation where we have the thermal expansion expression. So this would be the thermal expansion tensor. Here we have the compliance tensor. And here we have again another coupling introduced, the piezoelectricity tensor. And similarly, we have already a familiar material law here. In the last line, coupling dielectric displacement and electric field by the electric permittivity. And now we have again piezoelectricity here and pyroelectricity also. So what we will do in the next step is we'll assume the temperature so that the entropy remains constant. So we can simplify the equations a little bit and only get an equation for the strain and the dielectric displacement. And we've written them here already short in the tensorial form. Again, to remind you, the tensors are actually defined as these partial derivatives of the Gibbs free energy with respect to the respective quantities. And these can be considered to be known if we assume this linearized material formulation. So S is the compliance tensor, and E is epsilon is the permittivity tensor, and D now is the new coupling tensors. The symbols at the top actually denote at which quantity has to be held constant to obtain this tensor. And it can actually be shown that the piezoelectric coupling tensor is equivalent no matter if you hold sigma or E constant. So this is the equality condition you can use. So we'll, in the following, for the sake of simplicity, denote it by D only. And also note that the coupling tensors are rank 3 tensors since they relate vectors or rank 1 tensor to the strain tensor, which is a rank 2 tensor. And they are symmetric, so here is the symmetry condition. So in which forms can you write the constitutive law? The relations can be written in 2 different forms. One is called the D form. We have seen it already since the coupling tensor here is denoted D. In the related form, you can write if you express sigma and D, which is called the E form. So you basically rearrange the first equation to obtain sigma and also insert this expression in the second equation. And here are the relations that you can use that are used to relate these forms. As I said, simply express sigma from the first equation and insert it, and you will get the E form. The usefulness of the different forms depends on the application. For example, if we want to implement in the finite element formulation, we'll choose the E form, since in the finite element formulation, we have the sigma, and usually we want to insert our material law for the sigma in the balance of momentum. On the other hand side, if we do measurements, for example, and we apply sigma, and you want to, for example, measure the strain, then the D form might be more useful. So what structures do the material tensors have? I've given them here in Voigt notation, and be aware that these are for polarization in 3 direction. These tensors or piezoelectric materials typically show a transversally isotropic material. That means they have one plane where in this plane the material behaves directionally independent, so isotropic, and a plane and the direction transverse to this plane where the behavior is different. And typically this polarization direction determines the distinct axis that is normal to the isotropic plane for this material. So depending on the direction of the polarization, you have to orient your material properties in the correct way in the finite element model. So here are the typical form given for a transversally isotropic material. As I said, the 3 direction is the distinct direction. You can easily recognize this here if you look at the permittivity, which has 2 entries in 1 and 2 direction, and a different entry in the 3 direction. Okay, so typical values are given here for 2 technically relevant PZT variants. So just to have an idea of the order of magnitude of the quantities, I've given them here. So now let's look at the governing equations for piezoelectric phenomena. We have, of course, the mechanics equations are the balance of momentum, and we will assume small strains for the sake of simplicity in this course. And also we have the already known governing equations for electrostatics. We need to satisfy Faraday's law, so the curl of E is 0, and we'll do this by introducing an electric potential phi, and we also have to satisfy Gauss law for isolators, so the divergence of D equals 0. And these 2 equation sets are actually coupled in a volume coupling by the linearized constitutive relationships that we're using. So we have the sigma, which we will have to insert here in our mechanics equation, that is made up first by the mechanical quantity strain, but also by the electric quantity electric field. And similarly for the dielectric displacement, we have a coupling from the mechanical quantity strain and the electrical quantity. Okay, so we're ready to derive the formulation, the finite element formulation for piezoelectricity. As usual, the first step will be to introduce a test function for now each partial differential equation. So we have introduced u prime and phi prime, and we multiply is to our strong form and integrate over our domain. The next step is to perform the integration by parts. We do this, we have done this already several times. We use the product rule to rewrite the divergence terms and then apply the divergence theorem. And here, for the sake of simplicity, we have assumed homogeneous Neumann boundary conditions just to make the writing shorter. But for the case of inhomogeneous Neumann boundary conditions, you have the formulations for each of the PDE in the respective mechanic and electrostatic lectures. So the last step we have to do is to insert the constitutive relations and expressions for strain and electric field. And if we do this, we arrive at the common form for the mechanical equation. Here we have the mass matrix, we have the stiffness term, and now we have a coupling term in this bilinear form where we actually couple the test function u prime for the mechanical domain with the unknown function phi of the electric domain. And similarly in the electrostatic equation here at the bottom, we have a new coupling term where we couple the test function for the electrostatic equation with the unknown function of the mechanical equation. And of course, the weak form must be satisfied again for all test functions, u prime and phi prime. And this enables us to use the Galerkin procedure to derive the piezoelectric, the discretized system for the piezoelectric coupled systems. So how do we do this? We can again use standard nodal finite elements. We introduce ansatz functions for the unknown fields, u and phi, and then we apply the Galerkin procedure to arrive at the semi-discrete system of coupled ordinary differential equations. how does it look like for piezoelectric systems? We have in the first line the standard form for the mechanical equation, where we have in the unknown x actually the displacement degrees of freedom, and we have a second line where we have the electric potentials as degrees of freedom. Here note that the corresponding mass and stiffness and damping entries are 0. And we have in the stiffness matrix the standard stiffness matrix components from mechanics, so Ku, and from electrostatics, K phi. And we have the coupling terms, coupling stiffness matrices, Ku phi and K phi u, that come from the bilinear forms where we had the mixed ansatz functions from one PDE and unknown functions from the other PDE. So this is the typical form of the coupling blocks. So we have the gradients of the gradient of the ansatz function time our coupling tensor. This is the material property time the B operator in the of the mechanical displacements. Okay, so what are typical modeling assumptions and analysis types we can use to analyze piezoelectric systems? So the first assumption we take for the sake of simplicity is small strains in mechanics. We have also assumed linear piezoelectricity, so we do not consider the actually non-linear piezoelectric material. We also usually assume a perfect homogeneous polarization, so we assume the same coupling tensor everywhere in the polarized material. We typically assume zero resistance in the electrodes, so we can model the electrodes as a constant potential at the surface. And often you also assume them as mechanically not significant. So you don't model mechanically a metal layer there. You say this is very thin. I don't have to consider its mass or stiffness. So it's actually assumed as infinitely thin. And finally, we have, as for mechanical problems, a static analysis type, a harmonic analysis type where we compute the steady state response due to harmonic forcing. We can do eigenvalue analysis, and we can also do transient analysis and integrate the coupled ODE system in time. As boundary conditions, we also have the standard mechanical boundary conditions. These are standard, so we have fixed or surface tractions and so forth. We have the electrostatic boundary conditions, so zero resistance is usually assumed in the electrodes. So we apply a constant electric potential at the electrode surface. And often the electric network has an impact. So it's important to model electrodes which are short-circuited, so we don't know the potential there, but we know that this is an electrode surface. We have to specify a constant electric potential there, and this can be done via a constraint equation between these degrees of freedom. And finally, we have also the electric impedance, which is actually an output quantity. It can be computed from the displacement current density over the electrode obtained via, for example, the charge output. So the charge output integrated over the surface gives you the surface charge. And we know that the current is the time derivative of the charge. So this will give you the total charge is given by the surface integral. So the total charge of the time derivative is the total charge of the d field on the surface, the time derivative of it. And similarly, you can write this now in the frequency domain by expressing the time derivative by j omega, for example. Okay, and finally, what we need to specify when we analyze piezoelectric materials is the material rotation. As I mentioned already, the polarization is the 3 direction in the material direction, but it is not clear that the material defined in this 1, 2, 3 system is actually aligned with the XYZ system that you use for the analysis. So what you typically need to do is to rotate this 1, 2, 3 system into the XYZ system such that you actually analyze the correct material behavior. This can be done by, for example, using the Cardan angles alpha, beta, and gamma here given in the sketch. And this is in fact something you have to do all the time if you have anisotropic material behavior. So this is a very similar thing you have to also do, for example, for composite materials. Okay.